Okay, CNT140, we are looking at Chapter 7 on network cabling, so let's dig right in. One of the first things they mention here is, for cabling, they talk about must have a clear path between machines that makes for a good signal strength. In other words, basically a good cable run between, your machine and the switch in the closet kind of thing. And the other thing you need to have is a quality of signal. The signal is not distortable, so it's not usable. So our cabling system is going to try to accomplish both of those. A clear path, a really good cable from the user into the closet where the switch is. And the second one is the quality of that cable run needs to be good, so we have a good signal strength. So they stop for a second and they talk about a couple key terms. They talk about attenuation, impedance, capacitance, crosstalk, all important things when dealing with cabling runs. So let's break these down a little bit and understand a little bit what they're talking about. One of the first things they talk about is attenuation. Hopefully you remember this from 120. Attenuation is the weakening of a signal over a distance, the loss of signal power over the length of the cable. It's going to happen on any medium, especially in copper cable. And just think of it as, if you yell across a football field, if you're standing halfway across the football field, you can probably hear it and understand it. But on the far side of the football field, you can't hear it. The signal is weakening too much. So it's going to happen. It's going to happen through copper cable, especially. It still happens through fiber optic cable. This is measured in decibels per distance. In other words, that's the quantity we can say how much the signal has weakened over time. And they remind us that with copper cabling, the high frequencies attenuate quickly. So if you think that's through real quick, as we want to put more bandwidth through cable per time, we keep increasing the frequencies. That means as we start cranking up higher bandwidths through these signals are using higher frequencies, they're going to attenuate quicker. Okay, so it's kind of one of those keep that in mind. I put in here a little reminder about what your cable distance is. Yes, that's why they set the 90 meters max for horizontal cabling, and that's why as you're installing them, you try to keep them shorter if you can. They also mention that the cable construction affects attenuation. Better quality cable, better constructed cable will have less attenuation. Better constructed cable, if you will. So, with that, let me jump back here. I'm going to add to this more than the book talks about. The modern day term for attenuation is actually insertion loss. When we start testing our cable runs and actually certifying the cable runs later, we will see insertion loss pop up, not so much attenuation. It's a measure of the decrease of signal strength as it travels down the media. Absolutely. And if I look up in the standard, I'm not going to see attenuation. I will actually see insertion loss. And here is actually, I grabbed this out of our standard to show you on a horizontal cable run. They give us a maximum amount of signal loss that's okay for this cable run. And they show you with category 3, category 5, category 6, they show you the higher frequencies that are used and what is allowed as far as signal loss. So just kind of a heads up on that one. That's a more modern term. So there's attenuation, the weakening signal over distance. Watch your cable lengths, and your better quality cable should be able to handle that or be able to minimize the amount of attenuation or signal loss that you have. The next term they talk about is impedance. Okay, impedance is actually the total opposition to current flow presented by the cable. So this includes the resistance of the cable plus another function I'm going to talk about real quickly in a second here. The first one is resistance to the cable. Well, unshielded twisted pair cable is made of copper. Copper is an excellent conductor, but it still does have a little bit of minute resistance. So as I start making that cable longer, the resistance goes up a little bit. So the longer the cable run, the little bit more resistance I have. So that is going to affect the opposition to your signal going down through the cable. The second one is what's called the reactances. Well, they don't show you this in the book, but I want you to just kind of realize, and again, I kind of have this as a little, so you understand, you don't need to know this formulas, if you will, but if I were to calculate impedance, I run into a formula that, depending on the type of a circuit, it's going to factor in resistance, and it's going to factor in resistances, resistance and reactances. So depending on the type of circuit, I might have the square root of R squared plus X sub L minus X sub C, or X sub C minus X sub L. Anyway, I'm going to have all three of these pieces in there somewhere. And if I take a look at them a little closer, my inductive reactance formula is 2 pi FL, and my capacitive reactance is 1 over 2 pi FC. Well, what I am showing you this is, in either case, frequency is a factor in these reactances. As my frequency of my signal changes, it affects my reactances on top of the resistance. So and I point out here, important point 1, as the frequency of my signal increases, and I remind you to add more bandwidth, we're going to increase the frequency, the impedance of the cable changes. Hence, why the structure of our cabling, unshielded twist pair cabling, category 5, 6, 6A, 7, keeps changing to keep the impedance at 100 ohms. So if I take a look here real quick, the standard says a recognized piece of cabling that we can use is 100 ohm balanced twisted pair cabling. I'm allowed to use that. Well, they're saying right there it should be 100 ohms. So no matter what we do, we need to keep that impedance at 100 ohms. Well, that's why over the years, when we had category 3 cabling and had a little bit of signal through, and we wanted to add more signaling, the structure of the cable needed to change to keep that impedance at 100 ohms. So we twisted the cable more, a little tighter, if you will. We wanted to add more signal. We add the frequency, I should say the frequency goes up, therefore we need to change the structure of the cable, add our little separator here, to be able to keep it at 100 ohms. Hey, let's increase the frequency even more. Let's add shielding. Hey, let's add, let's increase the frequency even more. We add 2 layers of shielding, okay? So as we keep increasing the frequency signal, or the signal frequency through our cable to get more bandwidth per time, to keep this cable at 100 ohms, we keep changing the structure of the cable. Because, important number 2, the impedance of the components in the system must remain consistent. That equals the maximum signal transmission. So if I have a 100 ohm cable connecting to another 100 ohm cable, they match. So I'm going to have maximum signal transfer, if you will, between those two. If I don't have that, if I have a 100 ohm cable run connected to a 150 ohm patch cable, when those two meet, there's an impedance mismatch, and we're going to get signal reflections. As the signal hits that 150 ohm junction, some of the signal is going to bounce back, and we're going to get, dun dun dun, attenuation. Okay, so as we look at kind of the big picture here, I'm zooming back real quick. My impedance in my cabling is affected by the resistance and reactances, this stuff here, which gets affected by as I start increasing the frequency. So therefore, to keep our cabling at 100 ohms, we've been changing the structure for years now to be able to keep it at 100 ohms so everything remains consistently 100 ohms through our system. So therefore, we have maximum data signal transfer, if you will. Okay, so when they talk about impedance, they mention it kind of like in passing. Impedance is important, everything's 100 ohms. Absolutely, but there's kind of the nuts and bolts behind it. That's what they're getting at. So just realize that our 100 ohm cabling, kind of don't take that for granted, but also realize that's why the structure keeps changing on the inside to keep our cabling at 100 ohm impedance. And all of our system components should be 100 ohms impedance. Okay, so there's attenuation impedance. The next one they talk about is mutual capacitance. Okay, this is one of the main elements of insertion loss or attenuation. This occurs between your conductors inside the cable. It tends to filter out higher frequencies, and when that happens, it tends to round off our signal. Our signal, we're supposed to have nice square waves, if you will, an on and an off, or 1 and a 0. When we have too much capacitance, this rounds it off, and the other end has trouble reading it, so you get more errors, or a higher bit error rate is what they call it. Well, here's what we have happening with capacitance. If I have two conductors here, when there's they're close together, we can have signal here induce current over here, and that acts like a little mini capacitor. Especially the closer these are together. The closer they are together, they act like a little capacitor where they're actually trying to store the charge, not pass the electricity through. So one of the ways this has been compatted, if you look at, category 3, category 5, category 6, look at that. The little separator in there is to help with some of that issue, to keep them a little bit separated. So therefore, there's 6A, separator in the middle again, to keep those conductors separated to help with this capacitance issue, which in turn affects attenuation, signal strength. Okay, so that's what they're getting at with your capacitance there, and that's why, again, the structure of the cabling has changed over time, where we added the separator and then we're adding shielding and everything on top to help with that capacitance issue. The last term they mention out here is crosstalk, which hopefully you remember again from 120. And this is the amount of signal picked up by a quiet conductor. Okay, so if I have an orange pair in there and a blue pair in there, crosstalk would be some of the orange signal bleeding over to the blue pair. And that signal bleeding from the orange pair to the blue pair is crosstalk. That's what they're getting at. So when I have a signal bleeding from one wire to another one, or from one pair, if you will, to another one, that is crosstalk. And the main cause of this is poor terminations. Untwisting the wire too much and allowing signal to jump from wire to wire. And this happens at, I should say, all these terminations occur at the patch panel, at the outlet jack, at your patch cables. So any of those termination points where I'm untwisting, I can open up the possibility for crosstalk or allow crosstalk to occur. So just to kind of further add to this, because they only briefly mention crosstalk, so let me give you just a scotch more of info here, because you're going to see this again when we start testing our cabling. There is such a thing as near-end crosstalk and far-end crosstalk. Well, don't let that throw you. Near-end crosstalk is, when you're testing this end, if I hook my meter here, if near-end crosstalk is testing at the near end of the cable. Far-end crosstalk would be away from you, the far end of the cable run. Okay? So don't let that fool you or confuse you, if you will. That's what they're getting at with near-end and far-end. The other thing you also see is power sum. This is another test that's done where you have 3 pairs to another pair, where you actually have 3 pairs potentially inducing a signal into a single other pair. That's another test they do to see where I have a signal here. Is it jumping to the other 3, if you will? I think I said that backwards. I apologize. Signal here jumping to the other 3, if you will. So they're looking for that to occur out here. The other one that can occur is alien, where I actually have it between different cables. So this whole cable here is their signal jumping from this whole cable, all these wire pairs, to another adjacent cable. So we're not talking wire pairs anymore, we're talking the entire cable. They call that alien crosstalk. There is, as you can imagine, when I look in the standard, there's limits on how much crosstalk is acceptable. Okay, here is a horizontal cable near-end crosstalk. Instead of just near and far, I should say just crosstalk, here's a near-end crosstalk value. And this says, okay, for category blah, at signal level blah, this is the amount of allowable crosstalk. Okay, well, real quickly, if you look at it, it says minimum horizontal cable near-end crosstalk loss. Well, let's take a step further. I actually put in here a sample test result, and the pass-fail line is down here, and my signal level should be up here. What it amounts to is, and they even tell you here, a larger number is better, and my fail line is down here, so it seems opposite, but what it amounts to is a high decibel number indicates a strong signal with little crosstalk. So if I start with a nice strong signal and it stays nice and strong, I'm assuming then, therefore, the signal has not jumped ship and gone to another wire pair and been lost. So what you're always looking for is a nice strong signal to start and a nice strong signal to finish. If it weakens too much and you see it on another wire pair, you have too much crosstalk. So when it does, the signal drops over distance and it'll fall below the fail line. So in that case, a low decibel number indicates a weak signal with a lot of crosstalk. That's what they're getting at. And they say, okay, I should say the main cause is poor terminations, again, all those we mentioned before. And the main ways to stop this is watch your termination, half-inch untwist allowed at termination points, keep them nice and tight. And they talk about shielding, that you can have a foil shield, and here's 6A with a foil shield. That's one way to eliminate that. And or the braided shield. Here's a category 7 showing foil around individual pairs and braided around the whole cable, if you will. Those are ways to help prevent crosstalk. Okay? We'll come back to the next one about different types of cabling.